The title of his talk today is Modeling of Deformations for Tubular Organs Under Volume Variation by Biomechanics. So without further ado, let's welcome Dr. Go.
Yeah, thank you, Dr. Chen, for your introduction. And also thanks for everyone being here for the talk. So my talk is about the deformation for tubular organs. First, let's just have a short review for the typical tubular organs in our body. And as you know, there are so many tubular organs in our body. Yeah, some typical ones are like the blood vessels, and also there are lymph vessels, and the intestine, the trachea is the airway, also the human cervix, the female reproductive organs, and so on. There are many tubular organs in our body. And for those tubular organs, they have very important functions. Yeah, for example, they transport the air, like the airway, the trachea, and the fluid, like the blood vessel, also the lymph vessels. Also, they transport the waste out of our body, like the intestine, or other materials. And here, as you saw, the baby outside. So the tubular organs are like our body highway network.
Is it just me, or I'm actually not seeing the slides going forward?
Oh, I can see the slides. Can everybody else see the slides?
Yeah, can you see this, everyone?
Are you in the presentation mode?
This is a.
Can other people see the slides?
See, it's a PDF.
We're seeing a PDF, but we're not seeing the presentation mode.
Okay.
Oh.
So how should I change that?
What is it, because the PDF does not have the presentation mode? PowerPoint, do you have PowerPoint? Okay.
PDF can go to presentation mode. Just the question, so like, were you advancing slides or not before? So now we see when you move to the next page, right? But it's not in the full screen mode, right? So you can go to the full screen mode or whatever, but like, if you like, the easiest way is to just share the whole screen rather than like one application.
Okay. So now you can see me move the slide, right?
We see second slide, which is typical tubular organs. Right?
Okay.
Yeah, that's good enough.
So he's suggesting, can you share the
whole screen?
I think he is sharing the whole screen, and we can see the tabs.
Yeah, let me try this. Just
oh yeah, there is a full screen mode.
Can you see my slide typical tubular working now?
Yeah, I think this is good enough. Let's just proceed.
Yeah. Okay.
Can you see this slide tubular working structural properties? This slide?
Yeah, it's fine.
It's fine. Okay. Yeah, sorry for that.
Yeah, no.
Technical issues sometimes. Okay, so here in this slide, I showed some tubular organs like the blood vessels, and also this one is the lymph vessels, and also the tracheal airway, and the last one is the cervix and the female reproductive system. Okay, so now for the tubular organ structural properties. So for these tubular organs, there are many properties. I just summarize a few here. Mainly, so the tubular organs are composed of soft tissues. And the soft tissues are flexible to deform and can also maintain the structure of the organ. Also, the organs, usually it's multiple layers. One layer, 2 layers, 3 layers, like that. And each layer is different in the stiffness and the properties. And also there are fiber families in some layers. And the fibers are oriented in some directions. Sometimes maybe vertical, sometimes in the just circumferential direction, just around the disc like that. Also for the tubular organs, some ones are open, some ones are closed. For example, the airway is always open because we need to breathe air inside to our lungs. And also the blood vessels are always open. For the closed ones, like the esophagus, where we swallow food, it's closed. Only when it's open, when we swallow the food. Many other ones, like the cervix, it's also closed. There are also deformations for the tubular organs. So the deformations depends on the transportation. So it may become large and become small. And the last one, the pathological and untimely deformations can cause the dysfunctions of the organs. Yeah, so the deformations, if it's not in proper way, can cause some diseases. In this talk, I just show you two tubular organs, the trachea and the cervix, just as an example for the tubular organs. And for the trachea, it's easy to swallow because the inner layer for the trachea is very, very soft and can just accumulate water there. There is a disease called angioedema. For the cervix, cervix is very important for the pregnancy. And the cervix can become thinned, dilated, and softened, shortened, funneled, many deformations for cervix. So I just asked two questions for my research, before my research. The first one is how the deformation is formed under given volume change. So for the trachea and also the cervix, the deformation will change, but based on the volume variation, how the deformation is changed. Second question is, what growth is needed to form required deformation? So for the cervix, we want the cervix to be thinned, dilated, and softened, and shortened. So what growth is required to form such deformation? So these two questions are just my goal for the research. The first one, just a deformation for the tracheal angioedema.
So just a question, are you still on slide 2 or
are you moving to the next slide?
Yeah, now it's just the part 1 deformation for tracheal angioedema.
No, are you still on page 2?
Not seeing that.
What we are seeing is slide 2.
Yeah.
We're seeing your Adobe, like we're not seeing your presenter view.
Okay, I think there's a problem. Maybe I should not go into the full screen. Just can you now see my part 1?
Yeah. Yes.
Yeah, this is fine.
Okay, let's just do this. Sorry for that.
Okay.
This is my first slide, and then this slide, tubular organ structural properties, and then two tubular organs in this talk, trachea and cervix. Now this slide.
Yeah, now we see it moving.
Okay. So for the trachea, this is just the structure for the trachea. This is the whole airway system. And you can see for the trachea is this main part, and then 2 branches into the lungs. Above that, it's the larynx. So this one, the second picture is for just the main part of the trachea. And you can see there are many rings around the trachea, rings. The rings are, we call it cartilages. There are hard bones, soft bones. There are bones but very soft. This one can maintain the structure for the trachea. The third one is a cross-section for the trachea, cross-section. And actually, so below the trachea, here, this part, there's a flat part for the the ring, and below this one, this is the esophagus, so where we swallow food. And the last one is the enlarged, radially cut part of the real trachea. And you can see there are many layers. The inner layer, this one, is very soft, and the water can easily accumulate there. And then this dark layer is the cartilage and the soft bone part. So there is a disease called tracheal angioedema. It's the swelling of the trachea. There's a picture for the swelling, you can see. And then the two holes are just two branches into the two lungs. So when the trachea swells, you can see the lumen area may become small or large, and this will influence the air inside and outside of our lungs. And the reasons for the angioedema, here I just show you the three reasons. The first one is like inhalation of poisonous substances. So some ones are very allergic to some substances, like the peanut for some kids. This can cause the angioedema. The second one, for in bacterial intubation and extubation, for this one, so put some machine or equipment into the trachea to fix something. This can also cause the angioedema. And the last one is some other allergic reaction, like the flour, like that. And there is also one angioedema. It's caused by the genetics. So the parents have angioedema, then the children also have angioedema. And we call that one hereditary angioedema. So the mechanism for angioedema, it's like this one. In our the body, we have the blood vessel to transport blood and also the water into our body. There is also another system called the lymph system, the lymph. And the lymph system is not studied too much, but it's also very important. The lymph vessel is for balance of the water in our body. So if there is some extra water in the body, the lymph vessel will take away the extra fluid and take the water back to our blood vessel. So our body can maintain the balance of the water. So if we're healthy, there's a balance. So we don't have any swelling or water accumulation inside the body. But under some pathology or disease, the lymph vessel cannot work properly. So there may be extra fluid inside the body. Then the tissue will swell. And this is the mechanism for the angioedema. So for the modeling for this tracheal angioedema, first part, we use a idealized this cylinder, just 2 layers. And the second part, we study a patient-specific modeling. So by the structure for the trachea, the cross-section, you can see we have 2 layers. Inner layer is very soft. Outer layer is the hard, just a cartilage. So we model this one to be a 2-layered cylinder. And so inner layer is very thin, outer layer is thicker. And in the inner layer, we have the submucous tissues, and also there are longitudinally oriented elastic fibers. And the angioedema occurs in the inner layer because the tissue there is very soft and it can easily accumulate water there. The outer layer is uniform, cartilaginous tissue, so it's hard, so we don't have swelling there. And there's a deformation gradient. I know this is just for some common mechanics knowledge. And we have a map. So from the reference configuration to the deformed configuration, the capital X is any points in the undeformed configuration, in the reference configuration. We have a lowercase x is for the point in the deformed configuration. Now the deformation gradient tensor is the capital F equals the partial lowercase x, partial chi over the partial capital X. So this is actually a matrix or a tensor. The determinant of the F, so determinant for deformation gradient, there is a meaning for this one. This is actually the volume of the deformed configuration over the volume of the undeformed configuration pointwise in each point. So this is a volume ratio. So if there is a swelling or angioedema, then our DETF is actually bigger than 1. If there is no swelling or angioedema, then our DETF deformation determinant of deformation gradient is equal to 1. So the volume keeps the same. And now for the strain energy density functions and the cohesive stress, we use the Neo-Hooken energy function for the basic model. For outer layer, there is no swelling, so the WO is for the outer layer strain energy, just a common Neo-Hooken energy function. The inner layer, we have the swelling here, and the determinant for deformation gradient is V. So we update the Neo-Hooken model to be this formula, so WI, and then we have V here with the swelling ratio. If V is big, that means swelling is also big. And Q is a parameter, that means the swelling can change the stiffness for the soft tissue. Also, we have the fiber here, fiber energy. And the gamma here is a fiber stiffness. I4 is the fiber invariant. Then the cohesive stress is sigma equals Tn. T is just the cohesive stress tensor, and N is the outward normal of the surface. Then our cohesive stress tensor is by this way. This is also updated from the regular formula. Just we add V, the swelling ratio, to the formula. Now the deformation mapping, because our geometry is very symmetric, we also assume there is a axisymmetrical deformation for this one. So the chi deformation mapping is lowercase r of the capital R, the ER plus lambda z, capital Z, lowercase ez. Here the ER is are just the basis vectors. ER is the radial here. Here this is ER is the radial direction, and EZ is the longitudinal direction or axial direction. So there are basis vectors. And the lowercase r of capital R is the radial function. This one depends on the undeformed R location. And the lambda z is the axial stretch ratio. Okay. Anyway, so we use a capital letter R theta z for the undeformed configuration coordinates, and the lowercase r theta z for the deformed configuration. Then the equilibrium equation and the boundary conditions. For the undeformed configuration, we have the interface radius, the capital Ri, capital Rm, capital Ro. And after deformation, we have the lowercase ri, lowercase rm, lowercase ro. Then the cohesive stress tensor is T's, this one TRR, T theta, theta, TZZ. Because we're axisymmetrical deformation, we only have the diagonal matrix for T. The other parts are 0. Then the equilibrium equation is for the balance of angular momentum. It's this one. And then the boundary conditions. The first one is the inner and outer boundaries are traction free. And the axial force of the trachea in any cross-section is 0. And the number 3, the traction is continuous at the interface. And those boundary conditions are based on the geometry and also the surrounding tissue conditions for that. Because for the trachea inner boundary, there's only the pressure from the air, but we can ignore that because the air pressure then we go out and go down, and so there's average, so very small, so you can measure the air pressure on the inner boundary, like that. Then let's see some computational results. The parameters, we have the radius parameter for the Ri, Rm, and Ro, also the shear modulus mu I, mu O. Mu I is shear modulus for the inner layer, it's very soft. And shear modulus for outer layer, it's bigger since the tissue there is harder. Also the fiber stiffness, gamma. Those parameters are from other literatures. The parameters are also not fixed. Depends on gender, age, location, also experimental methods. So it's very different. We just use some ones, some typical ones. And there's a result for the Ri over, Ri is the deformed radius for inner layer. Capital Ri is just the radius for inner boundary in the undeformed configuration. So basically the vertical axis is for the inner radius, and the horizontal axis is for the nu for the swelling ratio. Now we can see that also Q here is just for to see how the swelling will change the stiffness. If Q is very small, it means the swelling will reduce the stiffness for the soft tissue. If Q is big, it means we will increase the stiffness, like that. So first, the swelling, if increases, swelling increases, the Ri inner radius will decrease first, then increase. So you can see that. And if Q is big, then it will decrease faster and then also increase faster, like that. And so just in summary, when swelling increases, the inner radius is not monotone or uniformly change, but decrease first, then increase first. This is just beyond our intuition. What we always think when there is swelling, the lumen will always shrink. It's not always true. Sometimes the lumen will also increase. If you have any question, you can ask. Maybe I talk to theoretically. There are so many mathematical formulas.
Maybe can you comment, so now you're trying to model the swelling of these tissues. So how much is known from experiments in biology, and how much you're either parameters or the swelling amount, right? The volume of the swelling volumes, or how much you're just trying to explore, what are the various possibilities for what you to try to explain what you see in experiments, right? So how much is known versus how much you're just trying things out?
Okay, that's a very good question. So for our these models, the parameters here are from the experiments from literature. For the swelling ratio nu, I just searched the literature, the references. There are not too much data values for the swelling ratio nu. And there's one, it's very small, it's around 1.2. It's very small swelling ratio. Maybe the swelling ratio is very hard to measure in lab. In our simulations, we use some just theoretical values. So you can see nu is from 1 to 14. Those ones are not so realistic, just for the simulation purpose. When nu is 1, it means there is no swelling, no swelling. You can see Ri over, lowercase Ri over biggercase Ri is just 1. It means the inner radius is not changed, keeps the same. So when there is no swelling, like that.
And in terms of your exponent Q, are these rheological properties of these materials known? You measure, you said that the shear modulus has been measured in experiments, but like this, like non-linear behavior, like stress strain behavior?
Yeah,
Stress
yes.
or something this has been measured?
No, no, sorry for that. Q is also just some assumed values. We want to see how the inner radius depends on the Q, depends on nu, the swelling ratio, like that.
And you mentioned you have fibers, like how are the fibers aligned? Like, are they like along the axis of the tube or are they pointing some other direction?
Oh yeah, yes. So for the fibers is in the inner layer and it's along the axial direction. The fibers. Those are just the collagen fibers.
Okay.
Yeah. Yes, our research is just mainly theoretical, and we need experiments to validate the models. And now we can only partially validate the model.
So follow-up question, is there a way to know which value of Q is closer to reality?
No, now we cannot. But we know there's one result. We know if there is a swelling, the tissue stiffness can change. But there is no relation how the tissue is changed. So just do some model. There's a parameter Q to just model the change for stiffness.
So maybe if there are some experiment data you can compare with, you can find out which Q makes more sense.
Yes, yeah, that's a good idea.
Hi, Kun. This is Steve. How are you? Thank you for presenting. One of the things that is a problem clinically, or at least a factor clinically, is that that flat portion of the trachea that you described is the membranous trachea. And it's a very dynamic component that responds to intrathoracic pressure. So it's something that I think is hard to ignore in modeling, and it makes the dynamics of the trachea, particularly with any degree of swelling, whether it's angioedema or a tumor or whatever the issue is, the membranous trachea is an important consideration, and it's important not just simply as a structure that accommodates intrathoracic pressure changes, but it opposes the cartilaginous rings in a cough. So that dynamic component is functional as well as just being a nuisance in terms of computational simulations. So it is something I think be important to at least think about down the road.
Yes, yeah, thank you for the suggestion. Yes, we just idealize so many things, so simplify too much here. Yeah, we can make the model more realistic. Yeah, thank you for the ideas. And so the next one is the patient-specific modeling. Now we extract the geometry from a real patient. And this is a software called Mimics, and we input just the photos, pictures for the body. Then it can produce one three-dimensional geometry for the body. And now we can find the trachea in this location, trachea. And also, this is another picture. We can see the trachea here in this one. It's very short. We can also use the software to extract the geometry for trachea. These are some pictures for the trachea from the patient-specific geometry. But we also need to do some manufacturing by our hands to produce the geometry, since the resolution for the pictures may not be so good. And then we can add the meshes, tetrahedral meshes into the geometry. And so there is a interface, inner layer, outer layer, and the meshes around the interface may be dense to produce the accuracy for the modeling. There's a results for the MPS stress. This one is the maximum principal stress. Okay. Anyway, this one is very time consuming. We need high performance computation to produce the results. And you can see the color. The red color means the stress is very high. The blue color means the stress is light. And also we have the S1, S2, S3, S4, for cross sections. And I can also see the stress distribution. You can see there is a S1, a red color means there's stress concentration there. And S2 here, there is a flat part. This one is just near the esophagus tube, so it's flat. S3 is in the lower branches, like that. Anyway, so this results will tell us where there is a stress concentration and where there is some deformation and a shape change. So we can know the tissue is vulnerable, and then we can treat there better. Yeah, that's the first model for the trachea. Then let's go to the second part for the cervix. The cervix in pregnancy, cervix is just a organ here. This part below the uterus, so below the baby. It's a mechanical valve to keep the fetus inside the uterus during pregnancy. So this organ is like a door. You can close the baby inside the uterus. And so the cervix here must be very firm and also closed in pregnancy to keep the baby inside the uterus. But near the due date, the cervix must be largely open enough to deliver the baby. So this is a very hard task. So the cervix must be closed before and open later. Very hard task. So there is a cervix evolution during pregnancy. The deformation is like softening, dilation, effacement, shortening, and so on. Here, the softening means the tissue is just very soft, and the dilation means the expand. I have one picture here. You can see in the beginning, it's very thick, and also the lumen is very small. Dilation here, you can see opening is very, very big. And also the wall is thin, so very thin. This one is to allow baby to come out near the due date. There is also collagen fibers in the cervix. And there are 3 layers for cervix, and each layer, the fiber direction is different. And near the due date, the fibers are become less oriented to reduce stiffness and also low density degradation and synthesis to increase water content in tissue. And there's one disease, and we call it cervix insufficiency. And this is a weak cervix. So cervix will softens ahead of due date. This will result in a painless preterm birth before 37 weeks of gestation. And this causes a miscarriage. So baby come too early, and we have the immature babies. So it's very dangerous. And so in the US, there are around 12.5% of all the preterm births are caused by the cervix insufficiency. And this costs around 500,000 babies annually in the USA, and it costs around $26.2 billion for the cost to treat the disease. For this one, again, we start with the idealized cervix. So three layers, cylinder. We can also add the ligaments around the cervix. Ligaments is just to attach the cervix around the body. And there are also fibers. You can see 3 layers. In the inner layer, there are fibers in the axial direction. Also, middle layer, these are just in the circumferential direction. Outer layer is also in the axial direction. Also, we model the cervix growth by hyperelasticity. And particularly, we model this one by the morphoelasticity. For morphoelasticity, we have a deformation gradient tensor F equals Fe times Fg. Fg is for the growth tensor. Fe is for the elastic deformation. Yeah. So the volume change is determined by the growth Fg, and the elastic is determined by the Fe. And for our model, we assume Fg is just diagonal. So we have the gr, g theta, gz, the three parameters in the three directions. And when the g bigger than 1, we call it a positive growth. When g less than 1, we call this the negative growth. So for g bigger than 1, the volume in that direction increases, so mass addition there. When g less than 1, this is a negative growth, and the volume in that direction, it decreases. This is for mass resorption. Okay, so again, we want to model the cervix thinning and also dilation in this research. And we define the cervix thinning by this way. So the thickness after deformation is less than the original thickness. When this happens, this is thinning. For dilation, we want R1 bigger than capital R1. That means the deformed inner radius is bigger than the undeformed inner radius. Also R4 bigger R4. So the outer radius is bigger than the undeformed outer radius. Anyway, so you can see it's very dilated. So we want the radius also be big after the deformation. So there is one result I tried in my simulation. Isotropic growth cannot reach the goal for the both thinning and dilation. We cannot. Now we consider how growth in each direction will produces deformation. So basically we have three directions: the radial direction, and the circumferential direction, and also the axial direction. Let's see for each direction how the deformation will change. For the radial growth, so GR is for radial growth. If GR is 1, then it means there is no growth. If it's less than 1 here, it's negative growth. Bigger than 1, it's positive growth. Okay, we can see for less than 1, there's a wall thinning. And I summarize the results here. GR. If GR is less than 1, negative growth, yes, there is a thinning, but no dilation. For GR bigger than 1, so 1.3, 1.7, positive growth, there is no thinning, no dilation. And for second one, the circumferential growth here. I summarize the results here. And for negative growth here, there's thinning, but no dilation. For positive growth, there is no thinning, but there's no thinning, it's just slightly no thinning. And dilation is also, dilation. So the G theta can produce both thinning and dilation for different growth. For longitudinal growth, axial growth, also you can see the bottom one is for the inner radius, almost not changed. So the result is for GZ, negative growth, we have thinning, yes, but no dilation. For GZ, positive growth, we have thinning, no. Dilation slightly, it's very, very small, very small. Okay. So we have the three radial, circumferential, and also axial growth, three directions. So what's the combination for both thinning and dilation? For thinning, we can have GR less than 1, GZ less than 1, and G theta less than 1. For dilation, we must have G theta bigger than 1. Because for dilation, only G theta can do this. So we use the circumferential growth for the dilation. And then we cannot use the G theta less than 1 in the thinning. For GZ less than 1, we can use this one as the cervix shortening, means the length of cervix can be shortened. We can use GZ for shortening. So as a result, we use, here summary, use negative longitudinal growth, GZ less than 1 for shortening, and positive circumferential growth, G theta bigger than 1 for dilation, and negative radial growth for thinning. So each direction has some kind of effect, and function result. Yeah, so some ones are negative, some ones are positive. So it's a mix of positive and negative growth inside the tissue. Also, we can use a three-dimensional modeling for isotropic growth under pressure from the above uterus. This one is earlier research still used isotropic growth. Just to show you quickly for these results. We have the energy functions Wm and also the fiber energy here. This is also for the compressible modeling. And we have the Tm and Tf for the stress from the soft tissue and also from the fibers. And this is formulas. I ignore the details. And also parameters from literatures. Boundary conditions. The top side, there are pressure from the baby's uterus and also the ligaments like AD, BC, EH, FG, MP, NQ, NO here. The ligaments are just a slip boundary. So you can slip up or down or left to the right based on your location. Also, this is a finite element computation. And we use some the methods like the principle of a stationary potential energy and also the Gattix derivative. Then last one, non-linear Newtonian method or Newton-Raphson method for the computation. So this one is the meshes. And these are some simulations. Also the color means the stress concentration. Just jump. This one is a cross section, viewing for the inside. The first row is for the pressure is 500 Pascal, and nu is for the swelling parameter. It's increase. Second row is for bigger pressure, 2000 Pascal, and also the swelling ratio is increasing. You can see for the pressure is bigger, then the top is actually more downward. Okay, and also the lumen, it's not uniform. Somewhere it's bigger, somewhere it's small. This is just a 2D result. The height and also the area of luminal opening, you can see, and also different colors are for different pressures. If the pressure is big, then the top is very low. The pressure will make the cervix downward. And the area around the cross sections on the height is also different. Somewhere the lumen area is big, somewhere it's small. It's non-linearly changing. You can see it's S shape. And this picture is for the also the height and for the area of luminal opening. This one, our pressure on the top is fixed, and the colors are for different swelling ratio. So if swelling is different, the height are always almost the same. You can see heights are all the same, but the areas are different, but they are very close, also the S shape. So the tables here are for also the swelling ratio and also the pressures. For each fixed pressure, you can see if the swelling ratio is small, then the top ascending is actually bigger. For the first three columns, you can see, but for the last two columns, if the pressure is fixed, then the swelling ratio bigger, then the top ascending will be also bigger. So it's non-linear behavior. The last table is the lumen length measure. There's a uniform change. If the pressure is small, then the length will be big, and if the swelling ratio is bigger, then the lumen length will also be big. And we can just apply the results to the cervix insufficiency to understand how the cervix will become short and descends is our results, just estimation for the results, and helps the cervix insufficiency diagnosis. And also we can know where the cervix is stressed, and help to use the cervix circumference. This is a method to treat the insufficiency stitch to strengthen the cervix. And also the luminal opening is highly nonlinear. This can explain why circumference may become loose. And so this one is just 2 models for the airway and the cervix. For the future work, we can study the micro scale to connect the hormone regulated volume changes with the deformations, where we can use more realistic modeling to add the dynamic pattern in the model like that. Also use patient-specific geometry for the cervix models. And we can connect it with the physicians to design tools to strengthen the weak cervix. And lastly, also in our team here, I can contribute my math and modeling skills to other members' projects in biophysics and microbiology. If you need any help from me with the math or the modeling, I can help.
Kun, just a question, like on this project, like do you know of the work of Christine Myers from Columbia University?
Yes, I know her. Yes, okay. I also read many of her papers.
Okay, yeah, I was just curious because, you know, like she's mechanical engineer and she has access also to clinical data and she's interested in the same problem. So
okay,
you may want to reach out to her, right?
Yeah, I may contact her to know more information and also for collaboration later. Some references and so that's it. So thank you for your time. It's a very long talk and too theoretical.
Great, thanks. Are there any other questions from the audience?
Yeah.
So just a question. So like, you know, like in these projects, so are you also actively working with like some biologists or experimentalists, or you're just inspired by the biological observations and you're trying to model them and explore what's going on?
So now we just work without the biologists, but I hope I can find someone to work together so they can validate the model and provide data for the models. So now the model is very theoretical.
Right.
Yeah. And also when I apply for grants, that's also a very big criticism. So I want more collaboration for the data and the experiments.
Yeah, I mean, especially because if you want to suggest, you know, some treatments or something, then you also need to know how, you know, your growth model will respond in response to some drug or some treatment or something. So you know, like that's usually very hard to know, like as a theorist, right? So you really have to work with experimentalists, right? So that you can get that data. Right?
Oh, yes.
Mm-hmm.
Hi, Quinn. I have a quick question before I have to leave at 3. Very interesting talk. The theory is indeed, you know, a little harder for me to digest as an experimentalist. So a quick question I have is, for some of this hyperelastic model, if you were to compare with some experimental data, what kind of data are you looking for?
Okay, that's a very good question. For the data, I'm looking for like the deformation, how the lumen area is changed, like the diameter for the lumen area, and also the thickness, the geometry change, like that for the tracheal airway. Mm-hmm. For the cervix, I want the data for the length for the cervix and also the lumen area, and also the thickness for the tracheal. Sorry, the cervix wall. Mm-hmm. Yeah, so thinning, dilation, the length, and also the stiffness for the cervix. That's very helpful.
Yeah, and I guess there are changes over time, right?
Yes.
Okay. Yep. Thank you.
Yeah, sure. Thank you so much.
Hi, Quinn. Can you go back to the slide with the fiber.
Fiber.
Yeah. So you have the slide that mentioned this fiber.
This one?
No, the one with the formula maybe.
Oh, okay. This one, right?
Yeah.
Okay.
So I was trying to understand when you have fibers embedded, how do you, like, does the elasticity of the fiber comes into play here in the equation?
Oh, so you mean how we make the fiber come into our equation, right? The models.
Yeah.
Okay. Actually, so you can see the fiber energies. We have the soft tissue, the isotropic matrix from Wm energy, and also the fiber energy psi, you put psi I4 here. So the two together, they form the energy for the cervix. And we derive our coherent stress tensor from this combined stress energy functions. Yeah. And actually our model is kind of complicated. The fiber here are evolving, so it's changing, stiffness are changing. And we also have a very complicated fiber model I ignored here in the talk. So together we are just determine the deformation for the cervix.
And what about the density of the fiber?
You mean the density for the fibers? Oh, and the density of the fibers will change the stiffness for the cervix. And that's the main function for that. So there is a parameter gamma. This is the fiber stiffness. Yeah, and the gamma can change. Yeah, so during the evolution for the cervix. So in the beginning it's very small. Then later in the pregnancy, near the due date, it's very, very, very small.
Cool.
Can I ask a question? I made it to your talk pretty late because unfortunately every other Friday I have a faculty meeting that goes till 2:30. But it's a really interesting topic and I'm really curious the parts that I caught. And I'm wondering, do you know if there are any biological hypotheses? So my understanding is the sort of last proximate cause of premature birth is ultimately cervical failure and insufficiency. Do you know if there are biological hypotheses connecting the stressors that are associated with premature birth to this sort of final step of cervical failure?
Oh yeah, that's a very good question. Actually, for the cervix insufficiency, we have many hypotheses. Yeah, for example, so the pressure on the top, so pressure from the babies, we are just press the cervix. And if the cervix is weak, this will make the cervix change the hormone distribution. And also the hormone will also change the soft tissue institution. And finally, so the cervix will become soft and so cannot maintain close to make the baby inside the uterus. So there will be a miscarriage.
So it's something like stress perhaps causes greater systemic susceptibility to those hormonal changes, perhaps would be a hypothesis.
Yes. So the hormone and the stress, they're just together have some association, but the relations are unclear. We don't know if it's hormone changing the stress or stress changing the hormone. And how the stiffness are changed, it's still unclear. And also the Meyer Christine in Princeton University.
No, she's at Columbia. She just gave a seminar at Princeton like last semester, so that's why I know. Yeah. But she has also developed like she has also figured out like how to like from just the images that doctors take, like how to predict the risk of premature birth and so on. So she has really gone quite far into
yes,
like understanding this problem, right? Like I don't remember all the details of what actually everything is involved, but maybe Karen can comment. She's Christine's
sorry.
college.
chiming in now. Yeah, so I really enjoyed your talk. I've been kind of watching someone else while a puppy while dealing with this. But